All right, so this is lecture 4, part 1 of 1. We're looking at the syllabus right now, and hopefully by now you have submitted your bio sketch. There's a little forum for that. I'm not going to do class time looking at it, but it's just something for me to see, where you've come from, maybe an idea of where you're trying to get with your career. So, and then summary 1 is going to be due a week from today. As I said before, it'll be late, the start of lecture Tuesday of week 4. It would be great to have some of those turned in by this time next week so that you can start your peer review and get everything wrapped up before lecture starts on week 4. Is that pretty reasonable? Okay. Anything else that you want to throw in there at all, Tim? Or okay.
Just for the tutoring.
Oh yeah, thanks. Yeah. So we are fortunate enough this semester to have a couple of one mathematician and one physical scientist who are working in the Learning Center as tutors. So Betsy
she manages it, and she
right.
can, if you need to make an appointment, Debbie does her appointments on Monday and Wednesday morning. She has an hour block that is just by appointment. The rest of it's walk-in.
Oh yeah.
So you can talk to Betsy to make your appointments.
Do you have those hours handy?
It is. It's the next one.
Oh, right here. Tutoring schedule. Perfect. Thank you. Nice. Little Word document. So Debbie Sloan, super person. It's funny. She's kind of high-strung and laid back at the same time. I mean, she's really driven by her discipline, but she's quick to crack a joke too. So she's available at the times noted. And then Trina's father is Richard Bayless. Richard was a faculty member here at Missoula College for a number of years. He's now teaching geology in China. So he's got a good, strong background in the physical sciences as well. So, if you're struggling with some of the problem sets or some of the concepts in the book, and Tim or I are not available, which we are, we're quite, making ourselves quite available. If for some reason you just want a fresh look at it, you can go see either of those two. Oh, and then one other thing. Today, I had the privilege of being invited by the Montana World Affairs Council to attend a presentation by a nonprofit named EcoViva. They've been working in Central America to develop renewable energy technologies, sustainable gardens, sustainable fishing, and they are going to be traveling to El Salvador this November. There's a chance they'll be looking for interns to come along and look at some of the problems they're facing. They'll typically employ Engineers Without Borders folks, so they'll have the local community present a problem and then go out to specialists like Engineers Without Borders. And I even mentioned that we have students looking for internships, chances to travel abroad and get involved in things like that, and they were thrilled to hear that. And then on a similar note, I was also asked by another organization to show you this. So this afternoon, I don't know, 4 to 5. I guess if you hustle over there after lecture, you could catch it, but New Zealand and Sydney, and Levi, you've spent some time in New Zealand, right? Probably vouch for what a neat culture that might be to explore. So if this is something that's interesting to you, hop on that opportunity as well. And I'm sure this will be recurring over the years too, so it's not just a one-time deal. All right, so with that, let's just dive into Chapter 2. Thanks, Tim. Get out of Energy 101, get out of here, get out of there. And so Tim's also been working on making the shell a little tidier, a little neater, and so that'll be coming online. You can see the archived lectures are here. I've been able to edit these. I see I have one little error here. I'd like to have lecture part 1 of 3 at the top, but that's something that Tim's been working on. So we started on chapter 2, last lecture. Let's pick up where we left off with that. And again, I'm going to focus primarily on the figures and fill in other places where they're maybe not as clear as they could be. Okay, so we looked at this briefly, and again, I mentioned the fact that this curve is a fourth order curve. It's the Stefan-Boltzmann equation, and I'm just going to throw that out here really quick. Stefan-Boltzmann's law. And so J in this case is actually power. You know, if we were going to write this in our engineering technology terms, we'd put a P there instead of a J, but sometimes technologists, engineers, and scientists have different symbols for the same thing, but there it is. There's your power. This is temperature to the fourth. And in this funny looking number right here, sigma, well, it's just called the Stefan-Boltzmann's constant, and it's got all kinds of wacky constants embedded in that. So you've got the speed of light right there. You've got Boltzmann's constant itself, which is fundamental to this first paper, this Solomon paper that we're reading, because it's in the dimensions of Boltzmann's constant are actually joules per Kelvin, energy per temperature. And there it is, sitting right there, energy per temperature. That's the speed of light. You've probably seen that before a bunch of times. That's meters per second. This guy right here is Planck's constant, and the dimensions of Planck's constant are actually joule seconds. So it's energy times seconds. Kind of weird, but that's what it is. When you mix all those guys together with your fifth power, fourth power, second power, you get this Stefan-Boltzmann constant, sigma. We know what all these are. We know what a watt is. We know what a meter is, and we know what a 1 degree Kelvin is. Here's the key component. See that Kelvin to the minus fourth? So it's temperature to the minus fourth. And when you take temperature to the fourth power, you get temperature to the zero. Like temperature sort of disappears from this equation, and all you're left with, check it out, watts per square meter. Perfect, because that's exactly what solar power is rated in, watts per square meter. So fundamentally, this little equation is sort of predicting this funky hump right here. So it's basically, tell me the temperature of my star, and I will tell you what its emission profile looks like. And it just so happens that our star is the right temperature, the right distance, et cetera, so that we're, basking in this nice sunlight that does our photosynthesis, that keeps us warm, et cetera. We talked a little bit about how these different absorption bands are the result of different chemical species in the atmosphere absorbing at different wavelengths. We also talked about once the energy hits the Earth's surface, which is only 15 Celsius or just shy of 300 Kelvin, it's going to radiate at a different, longer wavelength. And again, this thing, you can see how it curves here, it curves here, it curves here. You got three curves. That's a fourth order equation. Think back to your y equals mx plus b, your straight line, no curves whatsoever. It's because it's a zeroth order equation, zero curves. Okay, so that's how the math and the polynomials fall in line with this figure. Okay, so that is the energy that hits this planet as a result of nuclear fusion in the sun, which itself, believe it or not, is a result of gravity. So if you want to say, yeah, ultimately, yeah, the sun's power is coming from gravity. All of our technologies are gravity powered. Well, they are, because the fusion on the sun is driven by it. Kind of weird to think about. That's what it is. Okay, so that's some of the science. Now let's start to look at some of the technology. So right here, this is a solarimeter, sometimes called a oh my gosh, I used to say this word all the time. Pyranometer. There we go. Pyranometer. Yeah, and pyro is fire, so it's sort of measuring the fire of the sun. Pyranometer. Yep, there it is. And so what it's doing, it's measuring the total incident energy on the horizontal surface. So it's got this this half dome shape, so that, and I wish I had one. I almost bought one a couple of years ago, but couldn't quite justify the expense. But all of the energy basically above the whatever surface you're sitting on comes in and is integrated across really the majority of all of these wavelengths. So there are several different detectors in here. Yeah, probably it's not picking up little cosmic rays and all that. It's not picking up radio and et cetera, but it's capturing the vast majority of the energy in the belly of this curve, if you will. So when we get into solar PV later, it'll be important to know, well, gosh, how much energy actually is out here, and could you come up with a collector that actually turns those higher energy photons or lower energy photons into active electrons? And we'll get to that later in the PD, but something to think about when you look at these different technologies. Okay. Now, next, this is solar radiation on a horizontal surface, kilowatts per square meter per day. Now, let's first just do a little math here, and I'm going to throw a problem at you. Let's just say that our solar constant equals 1,000 watts per square meter. Give me an estimate of the maximum, well, let's look at the units again here. Kilowatt hours per square meter per day. What's the maximum kilowatt hours per square meter per day that you think you could get anywhere on Earth without really looking at this figure much? So max kilowatt hour per meter squared anywhere on Earth. Or, sorry, per meter squared per day anywhere on Earth. Take a second, do that. I'm going to pause the recording and we'll come right back. I just want to hear the numbers you come up with, and then we'll do it together. So I'm going to pause this guy and we'll be right back. Okay. Okay, so let's look at this. Let's look at this problem graphically. So we got a few different numbers thrown out there. So let's just look at well, here's the Earth. Here is 1 square meter, and we're looking at a constant of 1,000 watts per square meter. Now, this is just kind of an average, obviously, and if it's high noon and I'm sitting on the equator and this experiment runs for 1 hour, then so let's just go back to our equation. Energy equals power times time, right? Now, the curveball here is that I don't really know the power. What I actually know is the specific power. So what I'm going to do is define this thing as the specific power, and I'm just going to use the variable phi, right? Because I'm going to reserve the letter P for power, which is measured in watts, but I'm going to use the symbol phi for watts per square meter. Okay? So now, if I want to get from power, if I want to get to power from phi, what am I going to have to multiply it by? So I know phi is watts per square meter. I know that P is watts. What do I measure, multiply it by?
Time and square meters.
Square meters. Yeah, just square meters. So let's look at that. Now in this case, what do I have? I have the area equals 1 square meter. Boom, no problem. That's what area is. And now the power, let's just make sure the units work out. Power equals 1,000 watts per square meter times 1 square meter equals 1,000 watts. Boom. So now I can go in and use my standard energy power time equation. So let's just go from 11:30 a.m. to 12:30 p.m. Time equals 1 hour, right? So now I can run this energy equation one more time and say energy equals power, which is 1,000 watts, times time, which is 1 hour, equals 1 kilowatt times 1 hour equals 1 kilowatt hour. So we just ran it for best case scenario. I'm sitting there right on the equator, pointing right at the sun, and I'm going to, out of my 1 square meter, I'm going to get 1 kilowatt hour. Now, I heard a 16 thrown out there, I had a 12 thrown out there, and so if you're right on the equator, you're going to get 12 hours of daylight all the time, 24/7, 365, right? You might think there's a number, let's think another way. If you're sitting at the North or South Pole and it's during the solstice, you're going to have 24 hours of sunlight. So, right, if we're up here on the pole, we're going to be able to see the sun. Problem with that is you're not going to get the full 1,000 watts per square meter because you're kind of going through a lot of atmosphere. There's a lot of absorption. The truth of the matter is there might be times when you're getting well above 1,000 watts per square meter. In fact, I've seen 1,500 watts per square meter right out here in the back parking lot. And the reason for that is you'll have a lensing effect. So clouds in the sky will bend light waves and beam them right down like a magnifying glass. Kind of unexpected, but it happens. So you'll see a lot of fluctuations. So let's just kind of take this to its logical extreme, run the equator, and if we're going to go from, let's just say 6 a.m. sun up to 6 p.m. sundown, time equals 12 hours, and we're going to end up with 12 kilowatt hours on that 1 meter, approximately. And like I said, you might get a little bit more, a little bit less, but that's kind of your best case scenario. Okay, so let's keep that in mind, and now look at the next figure, and you can see that none of these numbers are really that close to 12 hours, because that's kind of your maximum. And so you would expect that, yeah, you move further and further north, and the maximum goes down. Well, what is going on here, though, and why are the lines so dang curvy? Why would it just kind of march up as a linear function of latitude? Where are the curvy lines coming from? Different altitudes is one, for sure, yeah. A little closer to the, little less atmosphere, more hours. What's the other one? Climate, yeah, clouds. If we go, in fact, we can look at Montana really quick. That's kind of a fun exercise. National. I think NREL has let's look for solar maps. Let's look at map search. This changes all the time, so let's take a quick look here. Customize this view. Map search. I just want to look at Montana really quick because we'll see something similar, and we'll see that in our part of the state we have kind of relatively methane emissions. Oh, it's all about methane right now. Tell you what, I'm just going to look at solar energy map Montana. Probably chances are somebody's actually got an image of this guy. Yeah, here's a good one. Oh, there's wind. Solar power resource. Yeah, this one's okay. Basically what we're seeing, there's sort of a corner has less solar radiation than the rest of the state, and that's just basically due to weather, just cloud cover, et cetera. So what your intuition there was correct on this one for Europe. Okay, but this is what the solar technologist is going to use to size a system. Someone's going to want to do solar hot water or solar PV. You're going to come to a map like this and say, okay, and your house is this big. This is how big you need to make your array so you can collect that much energy, right? So that's really all there is to it on this thing. It gets a little bit more subtle. We also, it can change drastically. If I took the data on the south side of this building versus the north side, I'm going to get almost no sunlight on the north side, right? But on the south side, tremendous amount. So this is just kind of what's hitting the average land mass. Once you kind of get down to the trees and the weeds in the building, literally, it gets a lot more interesting. We've got a solar pathfinder that we use frequently to make these numbers even more accurate than what we're seeing right here. Okay, so that's what this figure is all about. And as you just saw from my little online search, this data is available globally. So that's the resource. This is July, by the way. This is about as good as it gets in Europe for solar resource. And this is about as bad as it gets. Pretty cold and dark. So just fractions of an hour's worth of sunlight per day in some of those far northern climates. So this is why, I talked about a little bit last time how if you could devise a seasonal thermal resource, it could be quite valuable. Suck up the heat in the summer, store it somewhere, and then use it to stay comfortable in the winter. Because as we can see here, not a whole lot of solar resource this time of year. Okay, now another thing that we didn't really consider in our little back of the envelope calculation was what happens to that little square meter when it's not high noon. If thing's flat sitting on the ground, you're in good shape. But as you get into the 6 a.m., 6 p.m. Time zone, or as you move further north or south, you're going to want to tilt that angle so that it's perpendicular to the sun, obviously. If this guy was completely flat or horizontal, you would get no energy in it, right? If you turn it around backwards, same thing. So the tilt angle is critical. It's also worth noting that the energy scales like so. Let's just take a look at it really quick. So if the sun is over here and the earth is over here, and let's just put my panel at 0 degrees here, let's put it at 90 degrees here, and then let's put it at 45 degrees here. What I'd like you to tell me is what fraction I get at each point. So let's take another little math break and let's see if you can tell me what fraction of the sunlight we can get at each point. I know we did this in the practicum, so not testing you, but I know this should be a little bit of review. So obviously right here, what's the fraction here? Well, it's 1. What's the fraction here? Well, it's 0, because it's pointing exactly the wrong direction. This is 45 degrees. I want you to tell me what fraction of the energy we're going to get. First guess, you might say, well, it's halfway between. I'm going to get half. Let's see if that's right or not, though. So take a little time, do some math, and we'll be right back. All right, so here's an example of where some trigonometry is going to come in extraordinarily helpful. So you can look at this as either a sine function or a cosine function. Doesn't matter, you're going to get the same answer. So let's, we can call this 0 degrees. We can call this 90 degrees. And, well, I already told you this is 45 degrees. So let's just hop into Microsoft Excel a little bit and see what the sine and cosine functions do for each of these angles. Because the way to think about this thing is like, here it's maximized, here it's minimized. You know it's not linear. It's not a straight line. The Earth is curved. The Earth is circular. So, but here's an example of where the sine and cosine functions come in extremely helpful. We can get Microsoft Excel to behave. Maybe, maybe not. Yeah, I keep having the same issue. Let's turn some stuff off and see if that doesn't help. Okay, here we go. So I'll show you a couple little Excel tricks here. So I'm going to start with 0, then I'm going to type in 15, and I'm going to see if Excel can count or not. Let's try it out. Yep. It got to 90 just by dragging. So I'm going to put that in degrees, and then I'm going to come over here and convert it to radians. 2 pi radians in a circle. Pi radians in a half circle, so half a pi radians in a quarter of a circle, which this is. 90 degrees is a quarter of a circle. So equals radians. So Microsoft Excel has the radians function built in. And so I'm going to take degrees and convert them to radians. Now, if you remember, well, let's just do a quick check. Microsoft Excel also has pi built into it. So I'm going to say equals pi. Now, so pi itself is a function, even though we know it's a constant. So I'm going to put these closed parens on it and divide it by 2. Pi divided by 2 is 1.57, 1.57. So we can be pretty confident that our little conversions, we just double-checked Excel with Excel. I don't know if that's fair or not, but we can be pretty confident that 90 degrees is that many radians. Let's do one more double check. This is going to equal that number times 2, and there's your 3.14159, which you memorized a long time ago. Now, let's run cosine, and let's run sine on both of those. So equals cosine, open paren. So I'm going to click on that cell, close paren, enter. The cosine of 0 is 1. So going back to our figure, there we go. 0 degrees and 1. We're getting all the energy. Now, let's drag that bad boy down. If we take this, you're like, what the heck, e to the minus 17. Let's go in here and doctor this up a little bit. I'm going to do Control 1, which will get me into formatting. I'm going to click on number, and I'm just going to say 2 significant digits. And there we go, 0. So at 90 degrees, we got 0. Now, where are we at 45? Well, we're at 78%, almost 80%. Going back, so these numbers weren't that far off. I'm not sure exactly what formula you used, but using the trig formulas, this is going to be your most solid, straightforward first order approximation. Now, let's just complete it and say, well, gosh, I don't want to have 0 at the equator. I'd rather have 0 at the North Pole and 90 at the equator. Fine, we can do that. So this is going to equal sine, open paren, of our radians, close paren, dink. So it's just the opposite, 0. Sine of 0 is 0. Sine of 90 is 1. And the neat thing about this little exercise that we just did is that right at 45 degrees, you get the same number. And you can tell, so it doesn't really matter. You're going to get the same answer. And so that's how sine and cosine are related, and that's how you can sort of get it out. And it's kind of good news, right? I mean, you're 45 degrees away, but you're still at 70%. It's also pretty good news to know that, gosh, I can be at 75 degrees, and, well, I'm still getting 97%. Pretty good numbers. And so that's why a lot of times, you'll talk to these solar installers, like, do I put a racking system, no racking system? Within 15, 20 degrees, it's not going to make a whole lot of difference. You might dump a lot of extra expense into getting the thing tilted just right, but then you're kind of tripping over dollars to pick up pennies at some point. All right. So there's a little trig in action. Follow up on that figure. Now, not only and so obviously the Earth is tilted at 23.5 degrees on its axis, so you're going to get effects both as a function of time of day as well as time of season. There's your 23.5. So if you happen to be right there on the Tropic of Capricorn, Cancer, which one's the north? Capricorn? Been too long. Which one's the north? Capricorn or Cancer?
It's Capricorn.
Capricorn's north, Cancer's south, yeah. If you happen to be right there, you'll be getting that full 90-degree solar. Okay, now, obviously, as I was mentioning before, one can tilt one solar technology in order to gain better access. It's an extra level of complexity. Hopefully this semester we'll have a chance to look at our own solar technology. We've got it stored over at the Hive right now. There is a pretty nifty system built in. I'll draw it for you, where if we take a top view, and this is PV, but you could do it for solar thermal as well. There are two separate pistons and two separate collectors. So there's a piston over here, piston over here, and the whole thing sits on a hinge. So the whole panel, if we look from the top, it can rotate from side to side, from left to right, more or less. When the sun is here, it heats this cylinder and sends fluid to this cylinder, thus pushing, or that piston, thus pushing the panel in that direction towards the sun. Pretty cool. When the sun is over here, oh my gosh, it's a blue sun, but when the sun is over here, it heats this cylinder, which sends warm fluid into this piston and sends the PV array in that direction. When the two cylinders are the same temperature, it's in equilibrium and it just points right at the sun. So pretty cool, no electronics, no motor, combination of solar thermal and solar PV working together. Low maintenance, as long as you don't spring a leak somewhere. All right, we talked about this briefly. This is a very important figure. It's showing that glass will transmit all of this radiation, comes inside the building, but it doesn't go back out. So it comes in here, gets absorbed, it is partially re-emitted, but the majority of that sunlight bounces back. And there's a little table here, table 2.2 shows transmittances. You'll notice that those transmittances are much like efficiencies. They're going to be between 0 and 1. Again, there's only 3 things that can happen to a photon. It can be transmitted, absorbed, or reflected. In the case of solar thermal, where you want a lot of heat, you want a lot of transmittance coming in and very little going back out. So the selection of the glazing is important. You want the stuff to come in but not go back out. Best material I'm seeing right here is this polyvinyl fluoride, Tedlar, 92% transmittance, only 22% transmittance. Oh, I'm sorry. No, I think I got it backwards here. That's actually pretty poor transmittance at the long range. A lot comes in, but a lot also goes out. What you're looking for is a combination, that low iron glass, you're at 90%, but only 2% retransmitted. So in terms of solar thermal, that low iron glass is going to be your friend. Okay, just like there are 3 things a photon can do, transmittance, absorption, or reflection, there are 3 modes of heat transfer as well. They are conduction, and I'm going to have to dig into these a little bit here because they're very important. Sorry, I'm going a little bit long on this, but this is really important. Conduction, convection, and radiation. In the case of conduction, really the only thing that's happening is you're getting heat being transmitted by vibration. Might sound kind of weird, but hotter things are vibrating faster. And when a hot thing touches a cold thing, it gets that cold thing vibrating. Like literally, the atoms, the molecules in that material are vibrating faster. So conduction is just like one hot thing that's vibrating quickly, touching a cold thing and getting it vibrating until they're both vibrating the same amount, and then heat transfer stops. Convection is mass transfer. Notice in the case of vibration, no matter is being moved around anywhere. Mass transfer, what's a good example of this? Steam, wind, leakage out of your house. So anytime air is actually moving somewhere, that's why, gosh, in the winter you don't want a big gap under your window or your door because the air is convecting in. How about radiation? What's going on there? Photons, yeah. Do photons have mass? No. That's why it's fundamentally different. Are the photons vibrating? Yeah, but they don't really have to touch anything per se, but there you go, photons. So 3 fundamentally different modes of heat transfer. And those are going to be really important when we get into building energy efficiency and all that great stuff. Okay, so here's a figure of what's going on in a window. And this is why it's actually a pretty good idea just to put some drapes up in front of your windows, some kind of blinds, because what it's going to do is baffle these convective currents that happen inside the window. So heat flow obviously is going out the window in the winter. Warm air hits the window, hits the cold window, and heads down. Cold things drop. You can kind of think of the molecules as just marbles that don't have their energy anymore. They just kind of fall down, and there they go. On the outside, the window is going to be warmer than the outside air, so the convection happens in the opposite direction. If you had a little dust particles, you could see them moving up on the outside of the window. And then you also, inside that glazing, you've got basically the same thing going on. There actually is a little bit of circulation going on inside the window. Okay, and that's why you can see, well, having double pane, triple pane, et cetera, is going to cut down on those losses. Then the last thing, last thing I want to mention, and then we'll wrap this little bit up. This is kind of a long and important section, is the U value. The U value is the combined convection, conduction, and radiation losses. And what it is, it's actually the opposite. In fact, it's the exact mathematical opposite of the R value that you see all the time when you go to the hardware store and look at the R value on radiation. So U equals 1 over R. R equals 1 over U. They're reciprocals. It's just like in electricity you have resistivity and conductivity. Same thing. This is just the thermal analogy of resistivity. And you can even look at that R and say, oh, that's the thermal resistivity. That's exactly what it is. And the value U, what are they calling it here in the book? They don't even give it a name. It's just thermal conductivity is all it is. So, what are the units of U? We're looking at watts per square meter per Kelvin. Pretty cool, right? Because we've seen this before. This is easy, right? This is the same exact set of units that we were looking at in our solar radiation problem. So this is radiation heading out the window. Now, what's going on here? Why do we need that sucker on there? Wouldn't it be just good enough to know how much energy can flow through your window or your wall or your door or whatever have you? Why do you need that per degree Kelvin on there? Any idea? Intuitively?
Just at a higher temperature, more energy is going to exist in the space.
Yeah, that's how you want to think about it. So think back again to what I said about conduction and vibration. So let me just give you a quick little figure on that. So if I've got something cold here, and I've got something hot here, and let's just say that delta T, the difference in temperature, so if this is T cold and this is T hot, T hot, delta T just equals T hot minus T cold, right? And so when you run this, in fact, let's just run that little problem in box 2.2. And what it's asking us for, it says 2 square meters and a temperature difference of 25 C, right? So in the case of a window, let's just draw that little window. Very similar to the other problem we just did before. Area equals 2 meters squared. Delta T equals 20 C minus 5 C equals, am I looking at that right? Indoor and outdoor, 15, yeah. 15C, which, by the way, equals 15 Kelvin. The Celsius scale and the Kelvin scale have the same step sizes. 15 degrees C does not equal 15 degrees Kelvin, but a 15 degrees Celsius difference is the same thing as a 15 degree Kelvin difference, because the ladders on the rung are the same. So that's why I can get away with just saying 15C, 15K, same difference. Now, our power loss is going to equal our U value times our area times our delta T. And in this case, the U value given is 4.8 watts per square meter per Kelvin. So I'll start with 4.8, sorry, this is getting kind of small, 4.8 watts per meter squared per Kelvin. That's our U value. Our area is 2 meters squared, and our delta T is 15 Kelvin. So from there, the meters squared cancel, the Kelvins cancel, and we're just left with watts, and we're looking at 144 watts. Pretty handy, just to think of thermal loss as watts, and that's really the beauty, the magic, whatever, of energy tech, is you can always take it back to watts, and you can just, and what you can, then the thing to think about is that this is basically just one person power sitting there by the window, kind of radiating. Hey, Bob, go sit by the window and just radiate there a little. That's basically what it is. It's the thermal radiation equivalent of one person with this particular window. So you can see that you want that U value to be as low as possible, or, gosh, just get rid of the dang windows, right? Or, jack up the U value on the windows somehow. Or jack down, or up the R value, down the U value on the windows somehow. So everything leaks, sorry, but there it is. Okay. We'll take a quick break and then get on to the next section. That's a really important, very fundamental section in this chapter. We went over a lot of the physics, a lot of the science, and then dug right down into some of the technology and the math. So hopefully that ties a lot of the solar thermal together. Whew, that was a long half hour.